Okay, this is the last lesson in chapter 7. We're only going to do 3 lessons this week because we have a test, and then we'll have a quiz probably on this chapter the following week. What we're going to do is look at some of the formulas that come out of Newton's law of gravitation, and most of them have to do with planets orbiting the sun or satellites orbiting planets. And it's an exercise in using the formula because most of you are never going to actually have to calculate what the speed of a satellite would be, but it's interesting to see the way that this works out. One of the things that I should mention, and I think we talked about this once before, if I want to put something in orbit around the Earth, what I need to do is this. If we think of the Earth as having a curvature to it, what I want to do is shoot something so that it falls, and by the time it's done falling, it ends up being the same height above the Earth as it was before. Assuming there was no air friction, if I could shoot it at that speed, then this would continue going around. It turns out that the Earth drops 4.9 meters over 8,000 meters. So if you go out 8,000 meters, 8 kilometers, about 6 miles, the Earth actually drops about 15 feet. And so if you can shoot something at 8,000 meters per second, because that's what the falling rate would be, we would actually have something in orbit. Sir Isaac Newton reasoned that out. And because he had his universal law of gravitation, he was actually able to make the different calculations as to how fast things should go. So the first equation out of this chapter is this one. V is equal to the square root of g times the mass of whatever you're orbiting. Now, this is the hardest part for me in this section because your book will switch between the Earth, the Sun, or whatever. I'm going to put E here for mass of the Earth. But if they ask a question in the homework about putting a satellite in orbit around Jupiter, then this is the mass of Jupiter. So mass here is the mass of whatever's being orbited, divided by r. That's how fast you should have something going at a particular height for it to go into orbit. By the way, I should point out that if we had taken this same picture and I shot something exactly the right speed so that when it falls we're the same height, that will stay in orbit. Well, let's say I shoot it a little bit too fast. What's going to happen is this is going to leave the Earth, and if I don't shoot it far enough, it's going to eventually come back to the Earth. So getting a satellite in orbit means that you have to have exactly the right speed. This equation comes from our centripetal force equation. If you remember, there was an equation for centripetal force that was Fc is equal to mv squared over r. And that means that the centripetal acceleration was v squared over r, which means that v squared is equal to r times centripetal acceleration. But that centripetal acceleration in this equation, which is g times m1, m2 over r squared, or in this case, let's say mass of the Earth, this is m1 times g, and g is that centripetal acceleration. So g is equal to that. So if I put this in, v squared is equal to r times g me over r squared. Cancel it, and you can see if I take the square root, I get to here. So if they give you a problem And it doesn't have to be the Earth that you're dealing with. Like I said, they could be talking about when we sent men to the moon, we had to know what the moon's gravity was, and we had to get into a certain height. If you've ever watched, say, Apollo 13 or anything on the space missions, they had to do burns to get into the exact speed to be able to be in the moon's orbit. So if they give you the radius and what g is, then we're going to be able to figure out what the velocity would be. We'd also need the mass of the planet or whatnot. The period, orbital period, is 2 pi divided by the square root of r cubed over g times the mass of, again, whatever the planet would be. If you remember, we had t is equal to 2 pi times, we would have to go back. There was another equation for centripetal force, and the equation for centripetal force was 4 pi squared. Well, we had it up in the last one. If you work that out, you'll come out with this. This will tell me what the period is around whatever. And then around whatever we're orbiting. And then you would have this one, the g, I already had put this up, is g times the mass of the Earth over r squared. And that would be the acceleration due to gravity. And again, this is all assuming the Earth. If we're talking about some other object, if we were talking about what speed does a planet have to be in if it's so far from the sun, this would be the mass of the sun. Now, a couple of things about this equation right here. They're going to ask you a number of questions. And in fact, let's go even back to the universal law of gravitation. Okay. Sometimes people like to play a game, and they'll do this in the book, where they ask, well, what would happen to the gravity on the Earth if all of a sudden the Earth was twice as heavy? Well, if the Earth was twice as heavy, then the gravitational field, the pull of gravity, what we would experience as the acceleration of gravity, would be twice as big. What would happen if we kept the Earth the same size, but we doubled its radius? Well, in that case, gravity, even though the Earth is the same size, would be 1/4 what it was before, because 2 squared is 4, we're 1/4 of what it was before. What would happen if I doubled the size of the Earth, made it twice as big, but also doubled its mass? Well, in that case, this would be a 2, this would be a 4, and it would end up being 1/2 as much gravity, even though we have that much mass. So these problems, you're going to have problems out of the book like these. I'm going to spend some time on Wednesday going through those equations, but most of you will be able to figure these out yourself by doing them. One last thing, and I want to end with this. This will be a little shorter video. The concept of weightlessness is often quite misunderstood. You'll see pictures of astronauts in space, and we will say that they are weightless, and they actually are. Weightless, though, does not mean that there is no gravity. It could mean that, but around the Earth, this does not mean there is no gravity. Rather, if you had a person orbiting the Earth, an astronaut that we put, and we figured out exactly how fast to make him move so that he followed this path around. Essentially, what happens if you go back to this picture is that he is falling the entire time. He is falling. He is moving forward. If there's no air resistance, he won't feel that, and he is falling the entire time. He's falling but he's not getting any closer to the Earth. I tell students, in fact, I probably told you guys at the beginning of the year, if you want to experience weightlessness, jump off of a roof. I mean, don't actually do it, but if you did jump off of a roof, while you are in the air, you have no sensation of weight. If you jumped off on the scale and read the scale would read 0. That's because you are falling. So oftentimes people think, oh, there's no gravity out in space. No, there's plenty of gravity. The gravity is the same. If you're twice as far away from the Earth, the gravitational field is 1/4 of what it was before, but it is still a gravitational field. There's still a field there which is pulling you in. This equation implies that there is gravity because we have a gravitational constant R and ME. Actually, if I was to take and plot out what gravity looks like, if this is the Earth, we can actually think of the gravitational field exactly like we did with electrical charges. If I put an object out here, what's going to happen? It's going to fall toward the Earth. If I put an object here, it falls toward the Earth. And that falls toward the Earth, and so on. And that should look real familiar to you. And by the way, all of those converge at the center of the Earth, and that's why we would say that that's, in a sense, the source from which all the gravity is going. As you move out, move twice as far away, the area there is 4 times as large, and it represents the fact that that gravitational field is 1/4 of what it was before. One little note when you do problems. That they may give you a problem where they say, let's take one like this. We have the period, and they tell you we've got a satellite and it is orbiting at a certain height. Let's say it's orbiting the Earth at, by the way, the Earth's radius is 6.4. Just a second, let me pull this up. I should have this here. The Earth's radius is 6.4 times, no, that's not right. Sorry about that. The Earth's radius is, I should have that down, is 6.4 times 10 to the 6 meters. That's what I wanted to say, 6.4 times 10 to the 6 meters. If they say that an object is 3 times 10 to the 6 meters above the Earth, that's the height. But the radius of the Earth and the height are not what we're after. What we're after is this distance. So this is the radius of the Earth. Let's call that RE, and that's H. If they give you the height it is above, the radius that we're after is RE plus H. So in this case, how high would it be above the Earth? It would be 3 times 10 to the 6 meters above the Earth, but R here would be 9.4 times 10 to the 6 meters. Now, like I said, we'll go over some of those. I'll do some problems on Wednesday. But they're fairly straightforward, and some of you will be able to do them without any trouble at all. Anyways, so that kind of finishes up this little section on universal gravitation. The next section ties in. We're going to talk about theory of relativity, which is kind of interesting. That's really how we'll kind of end up the year. So, all right, that finishes this video, and that takes care of the lessons for this week.